Continuing Lecture 3 in the Computer Systems class. We've looked at logic gates and how we can add things up with logic gates, and we previously looked a little bit at how we can represent integers, whole numbers, or some of them anyway, positive whole numbers using binary. But integers also include negative numbers, and we also have real numbers that we might want to represent in a computer, so numbers with a fractional element, so 3.2, 0.01, 3.14 and so on. And we may also have some awkward numbers, such as repeating or recurring numbers, real numbers where the fractional elements contains infinitely repeating digits, so in decimal, 1/3 can be represented as 0.33333333 recurring, so the 3 keeps repeating there. Irrational numbers are a bit more awkward, so numbers with infinitely long repeating sequences, for example pi. So pi is a ratio that relates the radius of a circle to its circumference, but as you can see here it's a never-ending sequence, and it's not a non-repeating sequence. And that can create a big challenge for how do you accurately represent a number like that. So unsigned representations, and you can use these in many programming languages such as C or C++, allow you to use binary values to represent positive numbers. So you actually have a range of 0 to 2n, it's actually 0 to 2n minus 1. So that's another small typo, where n is the number of bits used to represent the number. So if n got 8 bits, well, it'll be in the range from 0 to 2n, which is 2 to the power of 8 is 256, minus 1. So there'll be 256 different values you can represent. So an unsigned 8-bit value can represent numbers between 0 and 255. What about negative numbers? How do we represent those? Well, we had quite a range of answers when I asked that question the previous week, but the simple approach is to use the first bit of any number to indicate that this number is positive or negative. And the normal form that would be used there would be to use a 1 in the first bit position to indicate a negative number. So the first bit is called the sign bit, because instead of representing a numerical value, it represents that the number itself is a plus or a minus number. It's a positive or a negative number. The remainder of the bits represent the magnitude, the size of the number. So with just 4 bits, 0011 would be 3, 1011 would be minus 3. And we would also have a plus 0 and a minus 0 value. So the range for 8-bit sign in magnitude, well, it would be minus 127 to plus 127. You can test that out for yourself. So 2 to the power of 7 is 128 minus 1, 127. And so you can go from minus 127 to plus 127. Some problems with this. Simple arithmetic becomes quite complicated with sign and magnitude representations. Using sign and magnitude representations, we can't easily feed in our numbers into a full adder circuit, for example, and get the right answer, because the binary addition doesn't reflect what's actually happening with the numbers that they're supposed to represent. So 0001 plus 1001, well, the binary addition for that would give you 1010, which is minus 2 in this sign and magnitude representation. So we might think we're adding 1 and minus 1, and we should get a result of 0, but the binary operations of a full adder would give us a different result. We also have 2 representations for 0. This might require some extra logic to test when 2 numbers are equal. So we need some special circuitry to work out how to add a negative number correctly. And we need special circuitry to test whether a value is equal if we've got a plus 0 and a minus 0 value here. So our first alternative is to use something called 1's complement. This uses positive numbers starting with 0 and again negative numbers. We're going to start with 1. But to get the negative of any number, instead of using the same magnitude and just putting a 1 in the first bit, what we're going to do is take the opposite value for each and every bit. So minus 3, instead of being 1011 for minus 3, we take the opposite value for each bit, and it becomes 1100. So this is called the ones complement. So complement basically means for each bit we take the opposite, the complement. So using 4 bits, find the binary for +1 and -1. Well, +1 is going to be easy, 0001. -1 is going to be 1110. What's going to be the result of adding these values? You can test this for yourself, but you should find that adding +1 and -1 happily gives us the result 0, gives us the correct result. There are still 2 values for 0, 0000 and 1111 will represent 0, but addition works as it should, more or less. This is one situation where we need to use the carry value, for example. So with ones complement, the carry value needs to be added back in as well to get the correct result from an addition. An alternative is to use something called 2's complement. This avoids having 2 representations for 0, also avoids having to carry the extra bit. To get a negative number, we invert all the bits as before, but then we add 1. So here's the process. So if we have the number 3 in binary, that is 0011. We invert the bits to get the ones complement, and then we add 1. And that value is how we represent -3 with 2's complement. 2's complement addition, I'll leave as an exercise. But for 2's complement, there's only one 0, and for 4-bit values we can see the maximum and minimum values. So the maximum positive value is 0111, is going to be 7, and the most negative value you can get is actually -8, so we can actually get an extra negative number in there. 1000 is -8 instead of being -0. There's another alternative easy way to find the negative of a number. Start from the right, find the first 1, and then invert all of the bits to the left of that. So we find the first 1 from the right, keep it the same, but then invert all the other values. So this 0 becomes 1, this 0 becomes 1, 1 becomes 0, 0 becomes 1, and so on. We have 2 examples here. So we start from the right, find the first 1, keep that the same, and everything to the left of that stays the same, and everything to the right is inverted. Allows us to work out 2's complement. To do 2's complement to decimal, the easiest way to do this is to simply convert from binary to decimal as a positive number if the first bit is 0. So we can tell this is going to be a positive number. There's a 0 in the first position. If there's a 1 in the first position, we know it's a negative value. So use the same process we've just described to invert it. So we can, basically here we keep this 1 the same and then invert all of these, and then we get a positive number of the same magnitude, the same size, but the positive equivalent, and convert that to decimal. And if you're on Windows 7, an easy tool we can use to check our results is the calculator. On Windows 7, the calculator has this scientific view, and we can use this. So taking this first one as an example only, what we're going to do is take the 2's complement of this to find what the positive number is. So programmer view is what we want, sorry, not scientific. And I'm going to input a binary number. It's going to be 0, 0, 0. As you can see, it doesn't actually show those. And 1, 1, 0, 0, 1. So that's the 2's complement of this first value. And then we can see what that is in decimal. It's 25. So this value must be -25. Again, you can do this by hand and use the calculator to check your results. So here's looking at this in more detail of how we would work through this. leading one, so we know it's a negative number, negate it to find the magnitude, start from the right, find the first one, invert all the bits to the left of that, and convert it to decimal. And as you can see, we get the same result as we got with the calculator, 25. And that's our solution. It's going to be minus 25 because we had a negative number. The next question I asked was how to represent fractional numbers in binary. So having seen how we can represent negative numbers, how do we represent fractions? There was a range of answers here, and I can see quite a few people had actually happily looked ahead and read ahead as requested. What was a little bit thin in the ground were nice clear answers where people being able to explain what it was instead of just naming it. There's a few different methods. Well, two main methods at least. Fixed point binary, fixed point float numbers is one approach. And with a fixed point, what we do essentially is we say, if we have so many bits to represent a number, we might say the first X many bits are the number before the point, and any extra bits at the end are numbers after the point. So if we've got a 16-bit number, for example, we could represent it as 12.4. So 12 bits and then 4 bits. So essentially we are adding to our representation, modifying our representation to say there is a point somewhere in the sequence of bits. So the bits before the point are the 1s, the 2s, the 4s, the 8s and so on. And the bits after the point are the halves, the quarters, the 1/8, the 1/16, and so on. So if we've got an unsigned 16-bit fixed point representation, the smallest value we're going to be able to represent, smallest positive value greater than 0, is going to be 1/16. The largest value, well, 2 to the power of 12, plus a half, plus a quarter, plus an eighth, plus a 16th. So it'll actually be a value just a bit under 4096, because remember the range goes from 2 to the power of n minus 1. So the whole number we'll be able to represent will be 4095 plus 15/16. And the smallest positive non-zero number we can represent is going to be 1/16, which is 0.0625. And here's our sort of fixed point challenge, which I gave the class. So with 8 bits after point, what's the binary for 0.75? Well, that's going to be quite easy. It's going to be 0.11 and then a whole string of zeros after that. So for 0.75, it would be 0.1 plus 0.01, 0.11. That's quite an easy one. And then the remaining bits would be 0 afterwards. 0.3125, well, don't get thrown off by this value here. 0.3125 is the same as 0.25 plus 0.0625, so the binary for this would be 0.0101 and then zeros after that. What about the binary for 0.1? And this is where it gets interesting, because with this binary representation, with 8 bits after the point, we can't represent 0.1. There is no combination of these values that can be used to represent 0.1. We can get close to it, but we can't actually get the exact value for 0.1. And that has consequences when we're working with programs and programming, we're working with numbers, is sometimes we can't always represent exactly the numbers that we're trying to represent. So we often think of computers as being amazingly accurate and precise calculating machines, but there are limits to their precision and accuracy with which they can calculate results. A whole range of algorithms and different methods have been created to come up with increasingly accurate results, but by default the results you get are not always accurate and correct. The alternative to fixed point representation, which has some limits because you're limited in terms of the largest number you can represent and the smallest fraction that can be represented, is to use something called a floating point number. Whereas the fixed point number, we said we decided that the point was going to be in a particular location. The floating point number, what we're going to say instead is we're going to use a number to represent where the point is. And it's going to allow us to move the point to allow for very, very large numbers by moving the point to the right, and also for very, very small numbers by moving the point to the left, so that all the digits come after the point if need be. But we can still have some issues representing some numbers. So, for example, to look at this in decimal first, to use a number system that we're used to using and is more familiar, we can break up a decimal number using a floating point. So we can consider the number minus 293.87, and we can represent this using values called the mantissa and exponent. So the mantissa is also sometimes called the significand, and this is the significant digits. The significant digits here are 29387. So we can represent this with a mantissa of 0.29387, just the significant digits. And then the exponent is telling us what to multiply that by to get the correct number. So if we multiply 0.29387 by 1000, that gives us our correct number. 1000 is 10 times 10 times 10, so 10 cubed. So the exponent here is 10 to the power of 3. So our mantissa times our exponent gives us our number. Now when we're working in decimal, the only value we need to remember for the exponent to store this is to store that it is going to be 10 to the power of 3. So the 3 here is actually the number we're interested in. So we've got a mantissa times 10 to the power of some exponent. Or for a small number, for example, such as 0.0000983, we have a mantissa and we have an exponent, and in this case the exponent is going to be 10 to the minus 4. You can hopefully imagine and see that we're going to be able to use this method to represent very, very large numbers and very, very small numbers using a limited number of significant digits and a separate value for the exponent. So the exponent value can represent a large number or a very small number. So 10 to the minus 4 here is basically saying we're multiplying it by 1 over 10,000, so we're dividing by 10,000. So we can also think of this as moving the point 3 places to the right. So move the point from here 1 to 3 places would give us 293.87. We can think of this minus 4 as moving the decimal point 4 places to the left. So it goes from being 0.93 to 0.093, 0.00, 0.000, and then we get our correct result, move the point 4 places to the left, 0.0000983. For our computer representation, we're going to use floating point numbers, but it's a binary representation again. So it's not decimal, it's binary. It's the same principle, but using binary numbers. So we're going to take any real number and represent this in 3 parts. We're going to start with the sign, same as before, a 0 or a 1 to say a number is positive or negative. An exponent, so is the number going to be a very large number or a very small number? How much do we want to shift the point? Where does the point get moved? Does it get moved to the left or to the right, and how much? And the remaining number of bits represent the significant digits of the number. The standard for this is the IEEE 754 standard, and you can read up on this online. There's lots of information. This most commonly uses 16, 32 or 64 bits, but it can use other values. And a relatively limited number of bits can represent a very large range from very, very hugely negative or positive numbers to very infinitesimal, tiny, tiny, tiny numbers. So here's, for example, how a float variable is typically represented in C or C++. You have 1 bit for the sign. The next 8 bits are typically going to be the exponent, and the remaining 23 bits are the mantissa. So that's the representation in 32 bits. Now the exponent itself is unsigned, so how do we get a negative value for our exponent when it's unsigned? And the answer is to use a bias. So the bias value can be subtracted from the exponent value to give us this negative range, negative to positive range. So if our exponent value is 0, it actually means to the power of minus 127. And if our exponent value here is all ones, well, that would be 255 minus 127 would be 128. So we can get a range of times 2 to the minus 127 or times 2 to the plus 128 for our exponent part here. And the mantissa is a 23-bit number, but we're allowed to have a leading 1, which gives us up to 24-bit precision in IEEE floating point. And we can represent very large and very small numbers. There's a few special values as well in IEEE 754, values for plus and minus 0. It's also got values for infinities. For example, 1 divided by 0, well, that's infinity. Not a number, so you can get a special sort of error number in effect if you try and divide 0 by 0. And when you're developing programs, results of the infinities or the not a number results can result in a program crashing. If you're using these in Excel, for example, Excel will tell you that you've got a result that's not a number, but it won't crash. But if you're writing your own code, you may need to be prepared to deal with results that are not valid numbers, and to make sure your program doesn't crash as a result of these values. There's a lot of reading linked to in the module references section in Blackboard, and the Principles of Computer Hardware has some very relevant and worthwhile reading on this. So hopefully this recording is useful, and I'll be back later with the recording for the week 4 lecture. Thank you.